Hello, and welcome back to video 3 for material energy balances, where today we're going to be going over homework 3. Okay? And the whole premise of homework 3 is a situation of three interconnected tanks with, we're giving some initial information. We'll deal with that later, but let's go over the gist of the problem first. And the end product is to use the simplest form of control, that being proportional control, to control the flow rate into the second tank for the three tank system so that we can maintain a fluid set point of 4 meters for the third tank. Okay? And I know that was a lot to take in, so let's visualize that really quick. Let's visualize that. Okay? So I've got a drawing written out and a equation that we start with. That's a rather important equation. Okay? That's the wrong tool. So let's go over the situation first. So we have three interconnected tanks, and they're all interacting with each other, which means that their flow rates and their height, therefore their height, each have an impact on each other, right? And we have one flow rate going in, and this flow rate we actually have control over. And the goal of this problem is to maintain a level of 4 meters for the third tank. Okay? So this is tank 1, tank 2, and tank 3. And the Q represents the flow rate, the volumetric flow rate. Between 1, 2 means between tanks 1 and 2. 2, 3 means between 2 and 3. And this is going out to the environment. And you can really imagine the environment as, a enormously large tank that will never have backflow, right? So, therefore, well, before we get started with that, let's quickly talk about this equation right here. And what this equation is saying is that the volumetric flow rate is going to equal our difference in height, or in other words, our apparent height, multiplied by a constant alpha. And that constant alpha, and you'll see in here, that constant alpha is the proportionality constant, and it's given in our problem statement. They're all 0.1 for simplicity's sake. Okay? So let's start with part 1, and we'll derive the differential equations to solve the fluid levels in the three tanks. Okay? And before we start thinking about differential equations, let's think about how can we define our flow rates using this equation. Well, why don't we start with the easiest one first? Okay, that's what I like to do. The easiest one first. And the easiest one is Q3, right? Because Q3 is going to only be dependent on I'm not using my laser. Because Q3 is going to only be dependent upon the height of the third tank. So therefore, we can say that Q3 equals the proportionality constant multiplied by H3 raised to the 1/2 power. Okay? Oh, I just realized. Oh, I apologize. This initial equation should have a 1/2 power here. Okay? That's a fatal mistake. Okay? And we'll move down the line. Next, we will want to discuss Q12. What's Q12? Well, I'm gonna make sure that I am in frame of the camera. Okay, that's good. Okay, what's Q23? Q23, okay, you'll see, is going to be dependent upon the apparent height between H1 and H2. Oh, I apologize. We're looking at Q23. It's going to be the apparent height difference between H3 and H2. And you're noticing now, like, hey, Quan, look, right, what you have drawn is H3 is higher than H2, but you have an arrow going that way. How on earth can there be flow that way? Well, we can account for that using math. You're very right for bringing that situation up, right? Because it's very much a situation that you can see in real life. So we'll account for that mathematically. Okay? So we'll say that Q2 is equal to, let's build this from the inside out, okay? The apparent difference between height 3 and height 2, we'll do this instead. Doesn't matter. It will not matter, and you'll see why. The apparent difference of height 2 and height 3 raised to the 1/2 power. And at this point, your gears are grinding, halting to a stop, and you're thinking, well, what happens if 2 is less than 3? Which right now it is. You're going to take take the radical of a negative, and therefore have an imaginary number. That's going to make no sense, right? So therefore, we're going to take the absolute value. Again, because we're only concerned with the apparent height difference, right? The apparent height that the flow rate will perceive, okay? But then this raises the question, oh, let's throw in alpha. Don't forget about alpha, the proportionality constant. You'll throw in the question, okay, if right now I'm arbitrarily defining my arrow as this way, okay? But if H3 is higher than H2, you're going to experience a reverse flow. Therefore, you will have, mathematically, you will see a negative flow rate. So what you want to do to account for that is to use the sine function, sine, and this is not like S-I-N-E, this is S-I-G-N, okay? It's different. Sine of H3 minus H2, multiplied by that, okay? And again, if you don't already know what sine does, it basically looks at the difference of H3 and H2, right? And it's going to say, okay, is it positive? I'll throw a 1. What's 1 divided by anything? It's the same thing. Is it negative? I'll throw a negative 1, and it will change the whole function to be negative, and therefore achieving a negative flow rate, which is what we want to see. Okay, so we'll apply the same principles that we just explained, okay, and apply it to Q12, okay? So H1 minus H2 alpha, H1 minus H2 absolute value raised to the 1/2 power, okay? And then one more special thing, okay? Qn, remember that Qn is something that we can control, okay? And we can control it using proportional only control, Qn. What's Qn equal to? Well, let's go to our problem statement, because guess what? It's given there. Okay? So, the simplest form, proportional control, the flow into the second tank is set equal to the proportionally constant, Kc, multiplied by the difference between the fluid level set point and the actual fluid level for the third tank. So, it's dependent on the third tank. So, Qn is equal to Kc times the fluid level H3 SP, the set point, minus the actual height of the third tank. Okay, let me double check, make sure I'm not missing anything. Okay, multiplied by the difference between the fluid level set point for the third tank and its actual value, just Kc. Oh, so, okay, we're all good. We now have all of our rates accounted for, right? So, moving on, we can now start thinking about our differential equations, okay? And what we want to model the volume of all of our tanks, right? How do we do that? Well, we know we are thinking about our height, and we know the cross-sectional area of everything. So therefore, we can say that, let's change color here. We can say that the area, and we're talking about tank 1 first, okay? The area of tank 1 multiplied by the dH1 over dt, in other words, the height as it changes over time, the height of the tank as it changes over time, is equal to the flow rate between tanks 1 and 2. Okay? The same principle applies for tank 2. Oh dear. The same principle applies for tank number 2, right? Where A2 dH2 dt is equal to Qn, right? You have flow rate going in plus Q12 minus Q23. Okay? And finally, for our final tank, we have A3 dH3 dt is equal to Q12 minus Q3. Okay, and there you have it. We now have our derived differential equations that models our three interacting tanks. Okay, welcome back, and let's take this moment to quickly explain what's on screen right now. On the left-hand side, we have essentially just took our problem statement and organized it into initial conditions and known information, as well as taking our derived expressions from my iPad that we just solved for moments before and put it into text form. So first and foremost, so that's easier for you guys to read. You don't have to read my chicken scratch. And second, so you can see, my expressions and my code side by side. Okay? There's one correction that is definitely worth mentioning, and it's a pretty fatal one, but simple but fatal one, and that being I dropped a negative sign there. The reason why that is negative is because the Q, that flow rate I designated, was leaving tank 1, so it should be negative. Okay? Without further ado, let's go ahead and get into coding. Okay? So, standard imports as always. And first thing I might want to do is to declare my initial conditions and known variables. So I'm gonna first declare my area. So A1, A2, A3 is equal to 0.5, 1, and 2. Okay? As is H1, H2, and H3. 0.5. That should be 5. 1, 2. Okay, and alpha is equal to, it's always equal to 1. There's no different versions of alpha. Okay? And I'll also take this moment to quickly speak about the SciPy integrate function. SciPy integrate.solveIVP function. So what it does is it solves an initial value function, right? And what does it want? It wants firstly, it wants a function, and that function is our right-hand side of our differential equation. Okay, so let's go ahead and do that. So we'll define an RHS function. Okay, RHS function, right-hand side of our differential equation. What does it want? Okay, what it wants is our independent variable, t, time, right, and a dependent variable. And it's going to be a vector since there's three, I don't know what the word is, a system, that's right, system of three differential equations. Okay, and we'll call it y for now. Okay, and we'll unpack it as h1, h2, and h3 as y. Okay, and I'll quickly demonstrate, okay, how do we know that t is our independent variable, and how do we know that h is our dependent? Well, just look at your differential equation. Over here, dh, dependent, dt, independent. Okay, next, what does it want? It wants time span. Okay, so it's going to be our initial time, 0 to some time, final time, and we'll call that tn is equal to 500. Okay, and then obviously it wants initial values to solve an initial value problem, and then it asks for a method. For our class, we'll be using the Radel method. Okay, and one more thing that we want to declare is that we do want a dense output. So let's firstly build our right-hand side of our equation. Well, let's do it backwards. Okay, we'll do it backwards actually. So it'll return the right-hand side of our equations. Return over here. Okay, first it's going to return negative Q12 over what? Over A1, because I'm taking that area and bringing it to the other side. A1. Okay, next it wants Qn plus Q12 minus Q23 divided by A2. Okay? Next, it wants Q23 minus Q3 divided by A3. All right? And let's work backwards here, okay? Next, we want to define all of our arrays, all of our Qs, okay? And we'll start with the Qin, because Qin is the Q that we can control. How is it controlled? Well, it's controlled by proportionality, proportional only control. It's controlled by Kc times H3 SP minus H3. what is all of that? Well, let me tell you. Kc is our proportionality constant. It's the value that you actually change in order to tune the controls, if you've heard that word before. H3SP is our set point. In other words, it is the level in the third tank that we want to maintain by controlling the flow rate in, right? And then the actual height, the actual level of our third tank. So let's define that. H3SP, the goal is to maintain a level of 4 meters, okay? And our Kc, we were given proportionally constant of 0.1, okay? Moving on, let's define Q12. What's Q12? Well, we derived it earlier. Q12 is equal to NP dot sine H1 minus H2 times alpha times double times NP dot ABS H1 minus H2 raised to the power of 0.5, raised to the power 1/2. Okay, then Q23 is much like the same, NP sine H2 minus H3, right, times alpha times NP dot absolute value H2 minus H3, right, raised to the power of 1/2. Okay, finally, Q3 is simply equal to alpha times H3 raised to the power of 1/2. And let me double check that with our derived expression on the iPad, and yes, that is correct. I'd hate to make an error now and, you know, come to the wrong conclusion, but let's move on. We now have our right hand side defined. So let's move on with using solve IVP. Okay? And remember, it wants the right hand side. It wants a tuple of our time constraint. Okay? It then wants our initial conditions, that being the initial height that we were given. And then it asks for a method. Again, we'll use Rodot method. Next, if we want to declare that, yes, we do want dense output, okay, equals true, and let's shift enter. And there we go. Success, true, great. And let me speak really quickly about the really neat thing about solve IVP. Okay, you can pull out a function from solve IVP called SOL, solution. Okay, so assign that to an object also named SOL, and what this now is that SOL is a function that will take in a dependent variable. Sorry, it will take in an independent variable and spit out a dependent variable. And this function is the solution to our differential equations. Okay? So let's go ahead and plot that so we can visualize it. Okay? So we first want to declare a t-plot, time for plotting purposes, and we'll use as always, np.linspace. I have no idea how many times those words came out of my mouth. np.linspace 0 to tn, and we'll put something like 500 spaces in between. Okay? Next, we want to unpack our solution, because recall that this solve IVP is taking in a system of three differential equations, and guess what? Solve IVP will actually almost always is dealing with systems of differential equations. Okay, so if you're trying to do this on your own with a different situation and you only have one differential equation and you run into some kind of error, keep that in mind. It may end up being some kind of situation where it wants something as an array. Okay, I don't know for sure, but it's something that's worth mentioning, right? So off of that tangent, we want to unpack our solution. So we'll call this H1 plot, H2 plot, H3 plot equals equals our solution object. Okay, and oof, what is it not liking? perhaps it wants t plot because it wants an array. That's right. You can't unpack. You cannot unpack. You can't unpack a function. Okay. So let's plot it. So fig equals make subplots as always. Subplots. Okay. Then we do fig dot add scatter x equals t plot y equals h1 plot mode equals lines and name we'll call it h1 plot. Okay. Repeat 3 times. Oh, I accidentally held down shift, but let's go ahead and change that. H2 H3 H2 H3. Okay. And there we go. Okay. Something is a little bit funny here. H3. So what we're supposed to be seeing is that we wanted our H3 set point to be 4, right? But it's not reaching 4. What's going on here? And then something is very, very funky here. Okay. So here's the problem. This is why I immediately started thinking in my head, man, what is going on? This is correct. We're okay with this. Because here's the problem with proportional only control. It's very flawed. You have to tune that KC in order to actually get close to your set point, right? But otherwise, this is the correct method and solution for modeling three interacting tanks with some initial values given by this homework statement and a KC constant of a proportionality constant of 0.1. And you can see how these curves flatten out, right? And this is a very important concept in chemical engineering. It's called steady state. And what's so important about steady state? Well, at steady state, all of our lines are flat. Therefore, all of our derivatives are 0, right? And nothing is changing, okay? And you can actually take these steady state values and then move on to another problem, right? And, you know, with that conclusion, I'm not going to go into PID controllers for this video, but PID controllers, proportional integral control, it's a way to get more accurately to the set point that we want of 4. Notice how the level of H3, it gets nowhere near 4. It's a very bad control, and it's something where you kind of have to tune the proportionality constant to kind of get closer, right? But then you kind of start running into some problems. Notice how, okay, yes, I'm getting a lot closer to 4 now, but what if my second tank only has so much capacity? Well, it's reaching almost 12 meters, right? And what if my first and second tank have a capacity of 8? Well, then we're gonna have problems. And then you can also see some funky things happening here. But otherwise, this is the correct solution, and it also is a great way to sort of display the problems with proportional only control, right? Well, with that out of the way, thanks for tuning in, and this wraps up homework 3.